Now, the final part of this week's online lectures. Let me start with a little bit of recap. We have encoded configurations of Turing machines by symbols having two parts. The top part consisting of the step symbols and the bottom part consisting of steps and a minus symbol. And if I add a separator hash to it, I can encode computation histories over this alphabet. Given M and W, we have defined set of all valid computation histories of M on input W as VALCOMP M, W, and we are interested in the complement of this language in delta star. Now I will show that this L is a context-free language. That means it has a context-free grammar, and the reduction Turing machine R that given M and W can prepare the grammar, a context-free grammar for L. Definitely this context-free grammar depends upon M and W. Given M and W, this language is fixed. And I can do it by looking at the description of M and W. It does not have to simulate M on W. Good. So, how does this conversion or reduction goes? So once again, let us look at the strings in VALCOMP MW, and then we will look at its complement. Okay. So, any string alpha and delta star that is in this set, we are of course interested in its complement, but for that we have to understand how we can fully characterize all strings in this. Then we will look at its complement. Okay. So, a string, you take an arbitrary string alpha from delta star, then that is in this particular set, VALCOMP M, W, if and only the following 5 conditions hold. Let us see. First, it must be of this form, hash C0, hash C1, hash C2 and so on up to Cn hash for some n greater than or equal to 0. Okay. And each Ci is hash free. It consists of pairs, okay, like tape symbol on the bottom half and either a state or minus in the bottom half or track. Second, C0, okay, so each Ci must contain only one state, one and only one state, not multiple states. So this Q will, one unique element of Q will come on the bottom track only once, all other things will be minus on the bottom track. Second, that is the second condition. Third condition, C0, the first configuration, must be the start configuration. And the fourth condition is that last one must be the halting configuration. Of course, we have assumed that the halting configuration may be reached somewhere in between. But if that happens, then that configuration remains constant. If Ci is a halting configuration, then I assume that Ci plus 1, Ci plus 2, all the way up to Cn are all the same as Ci. So it suffices to check whether Cn only is a halting configuration. Okay. That is the state of the Cn must be either R or T or R, accept or reject state. These 4 conditions are actually called syntax correctness conditions, syntactic correctness condition of alpha. Fifth one I may call semantic correctness. Each Ci plus 1 must follow from Ci using the transition rules of M. That is, if C0 is the initial transition, C1 must follow by one move of the Turing machine M on W. C2 must follow by one move of M on W. Okay, C3 must follow in one move and so on. Eventually Cn must follow in one move from Cn minus 1. So the first 4 conditions are actually easy to check because this is just checking for the correctness of the string, whether it is syntactically correct. Fifth one is, for fifth one we have to look at the transition rules of M. Okay, so now I define 2 important sets A and B. A consists of all strings over delta such that alpha is syntactically correct, that is, it satisfies conditions 1 through 4. Okay. And the second set is B, alpha in delta star such that alpha satisfies condition 5, that is, alpha is semantically correct. So a string alpha is in VALCOMP M, W if and only if it is both syntactically correct and semantically correct, right? So VALCOMP M, W is nothing but the intersection of A with B, right? Once again, recall that we are interested not in this but in its complement. In fact, this language is not context free. Its complement is context free. Okay. So if VALCOMP M, W is A intersection B, its complement L will be A complement union B complement. And I can write this way. This is same as this, A complement union A intersection B complement. So what are these parts? This A complement consists of strings over delta which are not syntactically correct. And this part contains all strings that are syntactically correct but not semantically correct. Okay. Now if I can prove one by one that this A bar and this A intersection B bar, they are both context free, then I prove that L is context free because context free languages are closed under union. They are not closed under intersection but they are closed under union. Okay. So it suffices to show that A complement and either this B complement or A intersection B complement are context free. Okay. But we will instead show that this is actually a regular language and this is a context free language. Okay. So a regular language is also a context free language. So both A bar and this will be context free languages and therefore we can generate a context free grammar for that. Okay. So the first task is I will show A bar is regular. But we know that regular languages are closed under complementation, so it suffices to show that A itself is regular. Okay. So there are a few notations I introduce. So let us say W is A1 through AN. This is the input string for this machine, Turing machine M, which is an instance of the complement of the halting problem. And we introduce some notations. Delta minus is a part of delta where the bottom track contains minus, the top track contains any symbol of from the tape alphabet of M. Likewise, delta Q where we allow only the states to appear on the bottom track. And 2 states are definitely distinguished. One is the accept state. So if we have T on the bottom track, we call that delta T. And if we have R on the bottom track, we call that delta R. Okay. So these are subsets of delta. Okay, the input alphabet for L. Now I write a few sub expressions, and then I will generate a full expression, regular expression for A to prove that A is regular. First of all, let us write a regular expression for the initial configuration. It must be of this form. If this is given, it must be this S A1 minus A2 minus everyone minus AN minus. Okay. So this is a sub expression that can be generated given W and from the knowledge of AS and the left in Barker. Okay. Then some intermediate configuration, beta I. It must contain symbols over delta, but only one state, delta Q. Before that and after that, there may be arbitrary strings, but on the bottom half or bottom track, I am allowing only minus. This is only one state. This is enforced by beta I, intermediate. I stands for intermediate. And final configuration must be a halting configuration. So this is an accept and halt configuration. So it's not an arbitrary state, but this state delta T. Otherwise, this gamma can be arbitrary. And before that and after that, only minuses on the bottom track. And likewise, the reject and halt configuration. If we have these sub expressions, we can generate a sub expression for A, all syntactically valid computation histories. So it is nothing but hash followed by the initial configuration, followed by hash beta I intermediate configuration star, hash, then either beta T or beta R, and finally another hash. So A can be generated by this regular expression. Just substitute these things here. Beta 0 substitute here, beta I substitute here, beta T substitute here, beta R substitute here. Okay. So A is regular. And since regular languages are closed under complementation, A bar is also regular. And we know that a regular language can be specified by a right linear grammar. So that is the first part. Next part is A intersection B complement is context free. So we assume that the input string is syntactically valid. We only want to check whether it is semantically valid or actually invalid, semantically invalid. B complement is invalid. Okay. So Ci and Ci plus 1 take two such consecutive configurations. Each has a preceding hash. Anyway, we want to figure out that Ci plus 1, the next configuration, does not follow from Ci. Does not follow means does not follow by the moves by a single move of the Turing machine M. Okay. Okay, so I use one important definition, a term. Two positions in Ci and Ci plus 1 are called corresponding if they are equidistant from their preceding hashes. Okay. So this is syntactically valid, so some hash must be there before Ci and some second hash must be there before this Ci plus 1. And if we skip the equal number of symbols starting from that hash, we get two positions, one in this configuration, second one in this configuration. They are called corresponding positions. Okay. We will see how we will use these corresponding positions. Now, what is important in this context is that change in a configuration is only local. It affects only a few symbols in this and this. In particular, we will look at three consecutive symbols in corresponding positions. Okay. Now, let us, in order to understand this, what is not Ci plus 1 does not follow from Ci, let us first see when Ci follows from Ci. So changes in corresponding positions, I mean 3 consecutive symbols that are consistent with the transition of M. Here are some examples. So no change. That means A, B, C, underscore, 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 A, B, C, remains same as A, B, C, underscore, underscore, underscore. That means the head is somewhere else and some transition is happening there. This part is unaffected. No problem. So this is a consistent change. Okay, no change is consistent. A state enters. So it's something like ABC minus minus minus, and this changes to ABC cube minus minus. This implies that something happens here. Okay, just the previous position, and the movement of head is right, so it comes here. Likewise, it may be it may enter here Q because something happens after C, immediately after C, and there is a left movement of the head, so this comes here. And if we have delta PB equal to QDL, okay. So here I am assuming it's a deterministic Turing machine. If not, there will be multiple possibilities for this. So we can handle all the things one by one. So it says that if the head is, if the state is P and head is scanning B, then this is B is overwritten by the new state will be Q. B will be overwritten by D and the movement is left. So B is overwritten by D and the state changes to Q and it comes to the left. So this is also consistent. Likewise, I have if delta P comma B is QDR, then the head moves right, state changes from P to Q, B is overwritten by D. So these are all consistent changes. So now let us look at changes in corresponding positions that are not consistent with the transitions of M. Here are some examples. This is not exhaustive, but we can generate an exhaustive list of all inconsistent changes in the corresponding positions. Let's say, for example, this transition function says delta P comma B is QD left. Okay. Then one possibility is it is overwritten by D, B is overwritten by D, and the head moves left, but instead of going to position, instead of going to state Q, it goes to some other state Q prime. Okay. So this is an inconsistency. The second thing, Q comes here, but instead of D, B is overwritten, is supposed to be overwritten by D, but it is overwritten by E, another symbol. So this is also inconsistent. Another inconsistency is like this. It is overwritten by D, state goes to Q, but instead of a left movement, this is a right movement. Okay. Likewise, we have 3 possibilities for right movements. Here, the state changes to Q prime instead of Q, and here instead of D it is E, and here instead of a right movement we have a left movement. Okay. And note that all combinations of these things are possible. The state is wrong and or the overwritten symbol is wrong and or the direction is wrong. Okay. So all possibilities are possible. Okay, are there. We make inconsistent things. Another inconsistency is if the state in some Ci is T or R, then that should stay the same in Ci plus 1. So if it is not the same, then it is also an inconsistency. Anyway, there are many other things. In any case, whatever you see that all these inconsistency patterns can be identified. Okay. In fact, given these and these, even one, I would say, okay, this is a finite number of things, only 3 things. Even a finite automaton can accept whether there is the change in consistency. There is an inconsistency, but we will require a PDA, in particular it stacks for a separate purpose. Okay. So instead of generating a grammar for this inconsistent change detection, I will generate a non-deterministic push-down automaton. Okay. So this works as follows. So this non-deterministically, this NPDA non-deterministically chooses two things. First, two consecutive configurations, Ci and Ci plus 1, and the corresponding positions. Okay, some positions equidistant from the beginning of these two consecutive positions. Okay, so I have a situation like this. The NPDA non-deterministically chooses. So before there is something, after also there is something, but it chooses some Ci, assumes that the inconsistency can be found here between Ci and Ci plus 1. Moreover, it also skips the same amount of symbols both in Ci and Ci plus 1. Okay, L, this is the same. And then it looks at this, and this to detect a consistency. Okay. So what does it do? So after the non-deterministic choice of from what to choose the Ci, after reading the hash before this Ci, this does the following things. It pushes some L symbols to its stack where L is non-deterministically chosen. Okay. Which symbol, it does not matter. It may be a constant symbol. U, but this stack is used only to skip exactly the same number of positions from here and here. So what symbol, it does not matter. So you just non-deterministically choose some L and keep on pushing those symbols to the stack, L symbols. Then there is a finite amount of information written in the 3 next cells. So store that in the finite control of the NPDA. To read the next 3 elements of delta, this 3 in the finite control. And then you simply skip this part. Do nothing on the stack, simply skip this part and this hash. Okay. Skip the rest of Ci and the next hash. Now you have to skip exactly L things. But you already have L symbols, so one by one pop symbols from the stack and move one step down. Okay. Keep on doing this, move ahead exactly L positions in Ci plus 1 by popping from its stack until the stack becomes empty, or more correctly some marker is exposed. Okay. And during this skipping the final, this last part of Ci and hash, the stack is kept unchanged. Okay. So this hash, the choice of I, which one is there is an inconsistency. This hash is non-deterministically chosen, and this L is also non-deterministically chosen, and the stack is used to match exactly the same number of symbols here and here. Match, of course, does not mean this is equal to this, this is equal to this, this is equal to this. You just keep L things here and L things here. Okay. Then you read the 3 next symbols and confirm inconsistency. So if the input is syntactically correct but semantically wrong, this means there must be at least one inconsistency somewhere. For some I, for some L, there must be some inconsistency. And this is the power of non-determinism. Since the NPDA can guess, it can find out that position of inconsistency. Right. So, to sum up, to wind up, what do I have proved? What have I proved? L, this is our language of interest, complement of VALCOMP m comma w, which is the union of A complement and A intersection B complement. We have seen. We wanted to prove that L is a context-free language. So we have proved. If alpha is in delta star, if it is in this set, there is at least one inconsistency. That NPDA of the last slide can non-deterministically find that and accept alpha. Moreover, this already is a regular language, so Weber has a right linear grammar. Now convert this NPDA to a context-free grammar, and we know context-free grammars or context-free languages are closed under union, so AL is a context-free language, it has a grammar. That completes the reduction from the complement of the halting problem to the set of all grammars, such that the language of this grammar is entire delta star. Good. So I would like to stop for this week at this point. This is already good enough for a week, and as usual there are some tutorial exercises. We are not sure what will happen with this online series of lectures, because we have not yet got any directive from the institute. So we are waiting for that. Depending upon that, we will see whether there will be a continuation of these online lectures or not. So see you. Bye.